In this video, I'm going to show you how to do particle analysis in image matrix. So this is the key part for any FM program, especially when you are interested in doing particle analysis. So I have covered how to do masking in another video called image correction, so I will not cover this right now. So basically so here is an image I open here. You want to process the image, make it flat, and before you want to do the particle analysis. So I'm just going to go ahead and flatten this image, and apparently I need more slightly do a secondary order flatten to make it look better. Do a mask flattening, and yes. Now I have the image pretty flat. So when you do particle analysis, you want to, well, you can do the whole image, analyze all the particles in this image. So the particle analysis is based on the mask of the threshold. So anything that's masked will be counted as particles. So if you have isolated masks like this one, that one, they count as two individual particles. If you have masks that's connected like this one, you only count as one particle. So depending on how isolated they are, you can have many particles, or if they are connected, you only have one particle. So in this case, I want to because this is an image of protein DNA complex, so the DNA apparently is not fully masked, and I want to decrease the stress level, see if I can mask them. So now I masked the DNA, so the DNA is connected, so they can be counted as one DNA molecule instead of two DNA molecules. That would be the case if the DNA is segregated by a masked area. So, and right now I have these. So the few things I want to do is, first, I don't want. I also observe that the surface is not complete flat, so apparently the second order does not do the work well. I probably should use a third order flatten. So what I'm going to do a flatten again, and yes, let's continue. I will use a mask flattening, do a third order, then click X. You can also do a Y direction flatten, which probably will take care of the issue much easier than X direction flattening. So right now, let's see. Okay, you see the noise is pretty much random, uniform at the ground level. So that means the surface is flat. So now I decrease the mask. I want to highlight the DNA as many as possible. I also want to have some noise there, just to illustrate how to remove those noise. So a key part of particle analysis, you don't want to have noise counted as real particles. You want to remove them. And the more noise you have, and it's more time consuming for the program to determine which ones are noise, which ones are real things. So there are several methods in image matrix to remove those noise. So you can check this box here. You can use filters or no edge. So the filters, we have the area filter and the volume filter, and later I will show you can also use the fiber length filter. So what that means is, if you use filters, that means that any area that's between the two boxes, which specify the upper and the lower bound of the specific parameter, like the area, you have minimum area and upper area there. So anything that's within this area, they will be analyzed. Anything that's beyond this region, they are counted as outliers, so they are excluded. So the same thing can be said for the volume. And this area and the volume, they are all in nanometer units, so they're not pixel units, so they're real units. So you can feel confident what you're choosing, put the parameters here. So so you can choose whether to use filters or not to use filters. If you don't use filters, so all these noise will be counted. So apparently you don't want them, so we usually use filters. And there's also whether you want to include the particles that's bordering the edge. So for example, like this DNA molecule, apparently it's truncated by the edge. It's evidently a 1 DNA molecule, but if they are truncated, it would be counted as 2 DNA molecules, so we don't want that. We really don't want to analyze anything that's not in full length, right? And this is truncated and not representing the real thing, so you can check this box, no edge, which means they are bordering the edge, the border, they're not counted, they won't be analyzed. So one thing you can do, well, at this stage, you can go ahead and click Analyze button, but you might want to do a threshold button. This is basically, it's not really anything substantial, but it gives you an idea like what's it's basically give you a preview of the results, like what's included, what's excluded. Otherwise, if you click Analyze button, it's analyzed. I don't know which. Well, I mean, you will know the results, but it does not give you a preview. That will be some kind of final results. If you want to go back, you have to delete the analysis and redo this procedure again. So the threshold function is really a preview. Now you can use the mask as the threshold, which basically use the current mask, which is the red color. And you click threshold, you'll see the results, and you'll see. So as you see that the noise are gone. Now the white area are the particles that will be analyzed, and also the DNA molecule that's bounding the border, they're gone. And apparently there's some DNA molecules that's not here. Apparently I use a volume filter on the upper range, which may truncate a few of my molecules. They are larger enough, they're not included, which I don't want that to be the case. So what I will do is I leave it empty, and then I threshold this again, and hopefully they will come back. Here they go, they come back. So so if you are uncertain, so you can simply go back to the mask by simply click the mask button there. So if you're uncertain like what's the range of area and the volume that you should choose, you can click the histogram there. And for example, let's click the histogram for the volume. Similar things will apply for the area as well. So you got a histogram of the volume distribution. That's basically the program does is it calculates the volume for all these mask particles, including the noise. So you do have a noise which is small volume. So you see they are pretty small at the lower end. You can specify the bin numbers, and they can slide the bar which default to 100 bin, but if you want a larger bin size, then you can, larger bin numbers, you can use, like for example 200 bin, you can specify them. And I do want to see like what's the area that, what's the volume range I should use, so I can zoom in this area. Let's see, yeah, I should do a horizontal zoom, but anyway. So as you see, there's a lower end 0, that's the noise, we don't want them. And there is our particles. I assume they're protein and DNA, so I will want to truncate this area. You can right click and use the current spot as the minimum volume. So this will automatically input a number in the minimum volume there. So that's basically determines the lower end of the volume that you should choose, because from the volume distribution, you know that this peak is what we wanted. Anything below that peak is just noise. So and the same thing can be said for the area. So right now, let's threshold again and see if this number is the magic number. So apparently, all the noise are filtered. So it gives you confidence that only your useful data, your particles, they're not filtered. So the volume is calculated. The area is basically is calculated using the pixels of how many pixels are in each of these particles, and then use the dimension of the pixels, specify the pixel x and pixel y. So this basically means each pixel right now here, each pixel in x direction is about 4 nanometers. So once you know how many pixels are in each mask, you times that pixel unit, like 4 nanometers, and which is like a 16 nanometer squared, right, to calculate area. So times that factor, then you get the real area. That's how I calculate the area in terms of nanometer square. So to calculate the volume, you need to know the intensity values. So the intensity, if you flatten the image, the intensity will be the corrected height of, it's basically the z value of the of each pixels within that mask. So basically, to calculate the volume, for example, for this particle, it basically calculates the area of that particle and times the average intensity within that area. So that's the intensity that's used to calculate volume. You can also specify the surface height. So what does that mean is you can specify a surface height, and usually when you flatten the image, the surface height is at 0 level, so it's basically 0. So you don't have to worry too much about that. So the surface is exactly 0. So your intensity, the correct value will be relative to the 0, to the surface value. So there's not much to worry about. But you can choose to specify any height to be your surface. So you don't want 0 to be your surface. You can, for example, specify the DNA, the average DNA height as your surface, right? The relative surface, it's all relative. So you can specify a number in the surface height box here. You can use the mask as the surface height. You just click the mask, it will use the mask size. It's basically duplicate this number in the surface box and use that number. You can also use the height from the intensity distribution, so which basically pops up the intensity distribution. For example, you can use the height. Let's do this. For example, you can use the height. There's some kind of shoulder there, which I believe is the protein DNA complex, and anything below that is the surface ground. For example, you can use the height at this spot, and then just click this, use current spot as surface height. This basically will pick up that number and input that number into this box as your surface height. So basically this means is you pick up at 4 nanometer, which is probably the lower end of your protein DNA complex, and use that as your surface height. This is usually the contour height of your molecules. But typically we only use the average number, which is about 0. Or you can use the peak location and use that as the height, which is pretty small. You can just leave it empty as if it's 0. So this is about the surface height. It's useful for calculating the volume. If you've already flattened the image, there's nothing to worry about the surface height. If you have other usage case, if you want to calculate the relative volume, for example, the relative height, you can specify a surface number. Regardless, the program will calculate both the real height, real volume that's relative to the 0 ground, and also calculate a height, height and the volume that's relative to the surface. So basically you get both. There's nothing to lose. So it's not like if you specify surface height, you don't get the real height, the height relative to 0. It's still calculated. So after I've done that, you can so the threshold, you can either use mask for your threshold. You can also use distribution. So this is basically nothing substantial as well. So you click threshold, it basically pops up a new window, and then you have an image on the left, and then the threshold, the results on the right. And you can move this bar. It gives you the threshold current level, which is like in real units, and it gives you the end results as well. So that's actually pretty neat, and it's basically a preview too. It's nothing. It does not add much compared to the other methods. So right now I have these. I will just let's see. I'll go ahead and let's go back a little bit, and then yes. So you don't have to use threshold. It's basically a preview. You can directly click analyze, and you can specify what kind of parameters to analyze. So there are options. So there are all kinds of parameters, so you can pick one or you can pick all of them. So the number of parameters will determine how fast you can analyze your data. The fewer, the faster. But if you use fewer parameters, you won't get the metrics of other parameters for one thing, and you may lose functions on some. You may not be able to use other functions in image metrics if those needed parameters are not calculated. So right now, usually I would calculate all the parameters, even sometimes you do not want all those parameters. You can just leave them. Just pick a few of them, and this will significantly fasten your analysis procedures. So I would just click Analyze with all parameters chosen. Apparently, something is still going to the threshold procedures. You can click down, but it shouldn't really go to that procedures. What I would do is I would click Mask. So in this case, if you just use Mask, it won't pop up in window. It just should really directly give you the results. So right now I have the analyzed results. So you see that the DNA molecules, if they are in the same color, which means they are connected. If, for example, these DNA molecules, they are not in the same color, they are segmented by different colors, which means they are not connected. This is the the usefulness of these specific color map. So basically, if they are connected, it will be shown by the same color. So I have all these molecules, and I could also see the original images. If you uncheck the Show Particle box, it shows you the original image. I can also hide the labels of these, the numbers, this text. So you can show selection, check this box, it hides them as well. And you can also click Show Fibers if you analyze fiber parameters. This is called fiber length. You specify any options. So if you click Show Fibers, you only show the fibers of that particle. What's the difference between fibers and particles? So let's see it clearly. So let me zoom in an area so you can see them clearly. So let me see, I can zoom in an area. So as you see that the particle is the blue and the fiber is the red dots. That's basically the skeleton of the DNA molecule. So fiber is really the shortest path between the two ends of the DNA particle. So yes, so it's basically the shortest path. So it really characterizes the length of the DNA, especially if you have a linear DNA, and it's basically a thinned version of the particle itself. So at this stage, let me go back to the original view. At this stage, what you can do is you can filter by fiber length. So originally I only filter by area and by volume. So after you have analyzed these particles, you can filter by fiber length. The usefulness of these, so threshold-based filtering, it does not exclude these proteins, and it does not separate the proteins from the DNA, because anything that's above a Z threshold value, they are analyzed, right? But using fiber length filter, you can specifically exclude the shorter fragments and separate the shorter fragments from the longer fragments. So to do that, you click the fiber length button, which lets you enter the minimum fiber length and the maximum fiber length. Basically, you have to specify a region. So for example, let me specify a region called it goes to 1 micron. So let's say I wanted to have the DNA is at 300 nanometer, which is e to the minus 9. So from 0 to 300 nanometer, what I can do with that? So I can remove those particles that's within that fiber length, which is cool if you don't want the proteins. Basically, the proteins is sure is smaller than 300 nanometer. All you can do is filter the fiber lengths, which basically those fiber lengths, the small fragments, they are shown, but the longer ones, they are excluded. They're not shown. This is not filtering. This does not filter the particles. It's only as a mechanism to read. It's basically for visualization. So and then you have added color labels. So let's do them both. See what the effect would be. So remove particles. They basically should get rid of all these proteins. So if you go with, it already removes all the proteins. So you see that's cool. And well, there's not much I can do. So let's do so let's click the fiber length again. This time let's not show the particles. So I already removed all the proteins, but as you see, we have DNAs, right? They have different lengths. Let's just assume this is a shorter DNA because, well, even though it's not connected, it shouldn't be the case, but let's assume it's a shorter DNA. This is a longer DNA. And there are usage cases where we want to separate those DNAs, the short ones from the longer ones. But sometimes if the DNA coiled like this is not a correct representation of that DNA molecule. But this is just used as an illustration, right? This sample is randomly distributed, but I'm sure there are other mechanisms that you can make the DNA align in certain directions, and that way you can basically sequence the DNA length using the fiber length filter. So let's just assuming that these DNA molecules are correctly traced. So what I'm going to do is I'm going to specify a specific region of the fiber length. Let's continue to use from 300 to 500 nanometer, for example. So this region of fiber length, right now you can use filter fiber length, which basically will remove the fiber length that's above 500 nanometer. That's really for visualization purpose. If you really want to focus on the small fragments rather than long fragments, you will just click filter fiber length. So only the small fragments are left, the longer ones are already moved. But you probably want a bit better results than that. Let's just go back and make sure I just use any larger numbers to make sure all of them are included. Let's go back again. So this time let's use this. Let's say 500 nanometer, which is e to the 7th. So I want them to be colored different, right? So the small fragments, right now they're all red, right? And this region will specify a small fragment. You can add a color label for it. Just add a different colors. So this is useful for visualization as well. So after you've done that, so you see that the small fragment will be colored green. And this is useful if you want to count how many short fragments they have and how many long fragments they have using their built-in cell counter in image matrix. So you can basically click this and say particle counter. This will basically pop up a new window. Then you can use color labels and the images, and then you can count how many small fragments they are and how many long fragments they have. And you don't necessarily have to use a file counter because the program would automatically give you the fiber length tables. They can just directly filter them in particle analyzer, which is not discussed in this video. So we'll cover that later in another video, and also for the cell counter as well. So when you are at this stage, you can show selections, and this opens a door to a number of operations. So you see here, you can select particles, the various operations, and you can also mark particles. So for example, if I mark the particles, what you do is you press Shift on the keyboard and then click the particle. This basically masks a circle on the particle, and it's really, it's basically a selection, a manual filtering method. So if you want these particles to be included, if it's clicked, then well, right now it won't be clicked. So apparently you have to show the fibers, because the fiber length is not a direct correspondence to whether the particles are filtered or not. What determines whether particles are filtered or not is the numbers, like the 2, 3, 1, 4. Well, numbers are pretty small here. I can make them bigger, and there are ways to do that. That's just to make them a little bit bigger, easy to see. Alright, so now we have these. So when you mark the particle, you then can say select marked particles or select unmarked particles, or unmark these particles. So I already have two tips for that, and they're easy to understand. So if you don't want to select this green particle, just select unmarked particles. So that particle gets removed. You can, instead of using marked particles, you can also directly select them. For example, I don't want this 3, they're not, because these DNA molecules you see here, they're not connected, they're wrong, they won't be useful. So you can just left click this particle and it's gone. And the same thing for that one as well. So basically these 3 particles, they're wrongly categorized. So once you have removed them, which means they don't have the numbers anymore with them, they are deselected, then the final step is to confirm your selection. So currently I only select 3 particles, have 3 particles removed. So you confirm the selection, then yes, then apparently there's another particle that's there. For some reason it's not getting removed. I will try again. Hopefully that's just, I didn't see it clearly last time, so let's confirm this again. Now it gets removed. So yes, so this basically is a final fine-tune procedure which you can manually remove basically outliers that's not correctly traced or categorized, or just, there are various image artifacts that you don't want to be included in analysis. You can do this final fine-tune procedures, just remove them manually. Well, this is not required if you do a particle analysis, because the outliers, they're not very useful. They are usually in the small number, and they can be easily categorized because they either have larger volumes, like they have erratic, lengths, and you can always exclude them from the analysis in the particle analyzer. So I don't really find them very useful in this part, but for some people it might be useful. But you can always exclude any of the particles, either automatically or manually, in the particle analyzer modules. So one last thing is, you can, if you are not happy with this current analysis, you can delete the analysis, and just click delete. You can choose whether to delete the analysis of the current one, or you can delete analysis for all images. Right now I'm not going to delete anything. You can also check the box called auto analysis, and that's pretty useful. I'll have to spend some time showing you this feature. So the auto analysis is useful because if you want to see results in real time, and that's especially useful. For example, let's see this. So I know that DNA is kind of long. They probably have larger volume as well. So let's see, maybe I can use 800 for the area. That's, I know from my experience, that's the number I use. So this should get rid of all the proteins and only leave the DNA. So when you click auto analysis, now what you can do is you can directly drag the bar on this, just a thresholding bar, and now it gives you the results as you drag the bar. So it automatically analyzes and it gives you the results. And of course the fiber length color bar and the color categorizing still remains as we set. So the green one will be the small fragment, and the red one will be the long fragment. So this will maintain and persist. So you can continue to decrease this. This is why it's useful. For example, because we know these particles, this DNA, they're not, they're not. There you go. So you see, as I adjust the mask area, I can make them reconnect. So for example, at this stage, at a higher threshold, apparently the DNAs get truncated. They're not connected. But at a small stage, they will be connected. So yeah, for some reason it's not showing, it's not removing these. So I suspect the program needs some time. So this is actually a time-consuming process. So often what I do is I would open parallel computing, which uses all the cores to calculate these. But I think there's some errors there. But the basic idea, I try to fix this later. But the basic idea is, as you adjust the threshold, you should be able to see the DNA reconnect. If they're not connected, right, they will be segregated. But you can continue to decrease the threshold till they reconnect. So this is useful if you want your DNA to be connected so that you can analyze them, so you don't have to exclude them from your analysis, because you want them to be connected to fully analyze their metrics. Yeah, for some reason, maybe let me see if I go up a little bit. I think it takes some time. I think right now it's working for, but it's not showing me anything. Let's go a little bit further. Oh, right now. So it takes some time. It's not very responsive. So as you see, after some threshold, the particles, yeah, then you can decrease this. Yeah, there's some kind of erratic. Anyway, so hopefully this will work properly in the future. Yeah, I think that's pretty much for particle analysis and image metrics, and hopefully you enjoy it.